Hello dear students, as you all know we were doing chapter number 12 and this is going to be the last video lecture of the chapter. Since we have done the chapter in the online live classes, this video is only for revision and let us start from the point where we have ended the last lecture, right? So the first point, the last point was we were doing that energy of a electron revolving in the nth orbit of any atom is given by E is equal to minus 2 pi square m k square z square e to the power 4 upon n square h square. In the last video lecture I have made a mistake also. It was 4 written. When I review the video I saw that it was 4 written. And earlier there was a 2 which was missed, because of that it was written 4, but it is actually 2. Okay, so please make that correct. E, this is the energy of electron which is revolving in the nth orbit of an atom which is having atomic number Z. For hydrogen atom, what we have done, Z is equal to what? 1, and if Z is equal to 1, then E is equal to what? Minus 2 pi square mk square Z is equal to 1. So it will be E to the power 4 upon n square h square. Okay, then after we have put the value of n as 1, 2, 3, 4 and we have calculated the energy of various orbits. So energy of the first orbit E1 comes out to be minus 13.6 electron volt, and from here if you put n is equal to 1, we have got the expression minus 2 pi square mk square e to the power 4 upon h square. So basically we can write this particular thing is equal to the minus 13.6 upon n square, that too with minus sign, electron volt. Okay, the minus 13.6 electron volt is the value of, if you leave this 1 by n square, so the minus 13.6 electron volt is the value of this which is written in the bracket. So we can write minus 13.6 upon n square into electron volt. E2 comes out to be minus 13.6 upon 2 square, which was minus 3.4 electron volt. Similarly, we have calculated E3, E4, E5, E6 till E6 we have calculated, right? So this is the thing which we have done. We have done all these things. Now let us move to the next topic, and the next topic is a spectral series of hydrogen atom. A spectral series of hydrogen atom. Let us start with that, and let us do it today only, so that the whole lecture is done. So, spectral series of hydrogen atom. Spectral series of hydrogen atom. Suppose an electron is getting transferred from N2 to N1. Electron is getting transferred from N2 to N1. So basically, according to the frequency condition given in the Bohr theory of atom, according to that, the frequency, the energy which is being released or absorbed is given by, delta E is given by En2 minus En1. Okay, En2 minus En1, what is the energy associated with the N2 orbit? Minus energy associated with the N1 orbit. Now the value of En2 and En1, value of E is minus 2 pi mk square. For electron, for hydrogen atom I am writing minus 2 mk square, Z is 1, e to the power 4 upon minus 2 pi square, n square h square. This is the value of energy. Okay, this is the value of energy. So from that equation, okay, we have just, will the value of n will be different, all the other values are same, so we can write if I take 2 pi square m k square e to the power 4 upon h square as common, so I am going to have minus 1 upon n2 square minus, because of this minus, and then minus 1 upon n1 square. Okay, when we put n2 we'll get this, when we put n1 we'll get this. This minus and this minus will become plus, so we can write 2 pi mk square e to the power 4 upon h square, and this delta E can be regarded as h nu. Okay, now that nu will remain like, oh, I have not written the bracket. Inside the bracket what will happen? Minus and minus will become plus. So let us write here, let us write it first, n1 square minus 1 upon n2 square. Okay, so now in place of delta E we can write h nu. H is transferred over that side and nu can be written as c upon lambda. Okay, so we can write c upon lambda. What is c? C is the speed of light. C is the speed of light. Okay, so c upon lambda is equal to, so it will be 2 pi mk square, z is 1, e to the power 4 upon h cube. This h, when it is transferred to that side, this h will become h cube. Inside the bracket we got 1 upon n1 square minus 1 upon n2 square. Okay, now c is also transferred to that side, so we get 1 upon lambda, and this 1 upon lambda is called wave number, which is denoted by nu bar, and nu bar is given by 2 pi mk square e to the power 4 upon ch cube, inside the bracket 1 upon n1 square minus 1 upon n2 square. Now this whole thing is called Rydberg constant, and it is denoted by capital R. So we are going to have finally nu bar is equal to capital R, inside the bracket 1 upon n1 square minus 1 upon n2 square. This particular expression you have studied, you must have studied in chemistry, but maybe in class 11th. Okay, so this R is called Rydberg constant. R is called Rydberg constant. Okay, and its value is 1.09 into 10 to the power 7 meter inverse. Okay, so its value is fixed. As per the electron is taking transitions from n2 to n1, accordingly the wave number will be emitted. Okay, and if wave number is known, then we can calculate the wavelength, and if wavelength is known, we can calculate the frequency. Is it clear? So this is how we calculate. This is the main expression which describes the spectral series of the hydrogen atom, and from where this expression comes, from here. And what is this? This is frequency condition of Bohr atomic model. Okay, so this is how these things are interlinked. If you are not clear with this, you will not be able to understand this, and if you will not be able to understand this, you will not be able to understand the spectrum of hydrogen atom. Okay, which is the main content of this chapter. Okay, so this is how the spectral series, from this expression it is explained. Now let us understand how many spectral series are there and how we are going to explain them. Okay, I am going to use that expression, that's why I am going to write that expression at the front, and then after we will start. So nu bar is equal to, we got Rydberg constant 1 upon n1 square minus 1 upon n2 square. Okay, and very important, here the electron is taking transition from n2 to n1, not n1 to n2. Although it is written 1 upon n1 minus 1 upon n2, but the transition is taking place from n2 to n1, not n1 to n2. Okay, so let us start with the first spectral series which we get from the hydrogen atom. The first spectral series is, first we get is Lyman series. Lyman series. Okay, What is Lyman series? Lyman series is there when N2 is equal to 2, 3, 4, so on, to N1 is equal to 1. When the electrons are getting transitions from higher energy states, from higher orbits to the first orbit, which is called ground state, then the spectral series we obtain is taken under the category of Lyman series. Okay. In this case, if we calculate nu bar, then it is going to be R. N1 is fixed, which is 1. So 1 upon 1 is square, minus N2 is varying. So we'll write N2 only, N2 square. And this particular spectral series belongs to ultraviolet region. Okay, this particular series belongs to ultraviolet region. This is the first series we get. Second series we get is Balmer series. Balmer series. In this, transitions takes from 3, 4, 5, so on to n is equal to 2. Okay, from higher energy states, electrons are getting transferred into the second orbit, to the second orbit. In this case, the wave number is given by, nu bar is given by the Rydberg constant 1 upon 2 square minus 1 upon N2 square. N1 is fixed, but N2 is not fixed, and this one belongs to visible range. Visible range. Okay, is it clear? Now let us move to the third one. Third one. Third one. What is the third? Third is Paschen series. Third is Paschen series. In this, electron gets transition from higher energy state 4, 5, 6, so on to n is equal to 3 orbit. Okay, n1 is equal to third orbit. In this case, the wave number is given by the Rydberg constant. N1 is fixed, 1 upon 3 square, minus N2 is varying, so we'll write N2 only. And this particular thing belongs to infrared region. It belongs to infrared region. Is it clear? Now, the fourth one is bracket series. Bracket series. In this, N2 is means from the orbit from which the transition is taking place. N2 is 5, 6, 7, so on to N1 is equal to 4. Okay, and in this case, the wave number is given by nu bar is equal to Rydberg constant 1 upon now, N1 value is fixed, 4 is square, minus N2 value is varying, so we'll write N2 only, N2 is square. And this also belongs to infrared region. Is it clear? Okay. And the last one, fifth spectral series, what we have to study is, fifth one is P-fund series. P-fund series. In this, transition takes place from 6, 7, so on to 5. Okay, transition takes place from 6, 7 means higher energy state to the n is equal to 5. And in this particular, the wave number is given by Rydberg constant 1 upon 5 square minus 1 upon N2 square, because N2 value is not fixed, and this also belongs to infrared region. So this is how, okay, this is how the spectral series are obtained. The first one is Lyman, second one is Balmer, third one is Paschen, fourth one is bracket, and fifth one is P-fund series. In chemistry, you must have studied more spectral lines, but in physics, we have to study only this much. Is it clear? So these are the spectral series we obtain. Now I am going to make energy level diagram for hydrogen atom, which is very important with regards to your board examination. Okay, so let us draw. So this is the energy level diagram. It is not completed. I have made only the lines because it takes lot of time. So I didn't waste the time while recording the video. These are the straight lines. Okay, this is your y-axis. This is your y-axis, and this is your x-axis. This one is your x-axis. Okay, this one is your x-axis, and this one is your y-axis. So basically, we have drawn negative of y because the energy is negative. The first energy level, which is n is equal to 1, you can see over here, which is n is equal to 1, and it is actually minus 13.6 electron volt. At n is equal to 2, it is minus 3.4 electron volt. N is equal to 3, minus 1.51 electron volt. N is equal to 4, 0.85 electron volt. N is equal to 5, minus 0.54 electron volt. 6, 0.38 electron volt. 7, minus 0.28 electron volt. Okay, these are the values of energy levels. Okay, so the Lyman series is obtained when electrons are getting transferred from higher energy state to the ground state. What is ground state? Ground state is n is equal to 1. So electrons are getting transitions from higher energy state to the ground state. So let us draw this ground state. Let us draw the transitions. This is the first transition we get. Then the second transition. Third. Fourth. From n is equal to 5. From n is equal to 6. From n is equal to 7. All these spectral lines, they belongs to Lyman series. They belongs to Lyman series, and basically they belongs to ultraviolet region. Okay, so here the photon which is released, it is actually of ultraviolet region. The second series we have studied is Balmer series. For Balmer series, electrons are getting transitions from higher energy state to n is equal to 2. So the transitions will be like this. Sorry, it should be here and it should be here. So this belongs to Balmer spectral series, and the photons which releases from here, it belongs to visible region. Okay, these are visible. Now the third one is Paschen series. Paschen series is when the higher electrons are getting transitions from higher energy state to n is equal to 3. So from n is equal to 4 to n is equal to 3, 5 to 3, 6 to 3, 7 to 3. They are called Paschen series. Okay, and they belongs to, if a photon is released from here, so this belongs to infrared region. Okay, IR stands for infrared. Now after Paschen we get bracket series. For bracket, electrons are getting transferred from higher energy state to the n is equal to 4 orbit. So this is your bracket series, and the photons which releases from here, it is also infrared region. Okay, and the last one what we have to study is P-fund series, when electrons are getting transferred from higher energy state to the n is equal to 5. Here the photon releases of infrared region, and this is called P-fund series. Okay, so this is what we call energy level diagram of hydrogen atom. Okay, this n is equal to 1, it is referred as ground state. it is referred as ground state. This n is equal to 2, it is referred as first excited state. First excited state. This referred as second excited state. Same goes with 4. 4.1 is called third excited state. Okay, 4.1 is called third excited state. Okay, fifth one is called fourth excited state. Sixth one is called fifth excited state. Means the number is one less. Because the one is called ground state, it considered as 0. So it will be first excited state, it will be second, it will be third, it will be fourth, it will be 5, it will be sixth. Okay. Now there are some points which we should remember while making this energy level diagram. What are the points? Let us see. Let us see. First of all, if you notice, then the gap between the lines keeps on decreasing. The gap between these two lines is quite greater than gap between these two lines. Gap between these two lines is greater than gap between these two lines. Basically, the gap is going to decrease. Why is it so? Because you can see it from the energy also. Its energy is minus 13.6 electron volt and its energy is minus 3.4 electron volt. The difference is approximate 10 electron volt. Okay. And now this is minus 3.4 electron volt, this is 1.51 electron volt. The difference is of approximate 1.5 something, 1.5 electron volt. Now this is 1.51 electron volt and this is 0.85 electron volt. Difference is approximate 0.6 electron volt. Here it was 10 electron volt, here it was 1.5, here it is 0.6. And if we go higher, then the energy between two lines keeps on decreasing. The energy gap keeps on decreasing, and that's why the lines, as we go higher state, the gap between the lines are becoming smaller. The highest line which denotes the zero energy level, it denotes actually n is equal to infinity. It denotes n is equal to infinity. When an electron is excited that much, when it goes to n is equal to infinity, we'll say that electron is free of the atom. And for making it free, if the electron is in the first orbit, means in the ground state, how much energy is required to make its energy 0? This is your 13.6 electron volt. So this particular energy, 13.6 electron volt, is the required energy, okay, which is the energy which should be given from outside to make the electron free from the atom. So this energy is called ionization energy. Ionization energy. So how we define ionization energy? We say that the energy required to make an electron free from the atom from the ground state is called ionization energy, and its value is for hydrogen atom is 13.6 electron volt. Now if we want to do the same with some accelerating potential, then what is the potential required? Potential required will be 13.6 volt. This is the kinetic energy which is given to the electron by applying a potential difference of 13.6 electron volt. This is called ionization potential. Ionization potential. Okay. This is called ionization potential. Is it clear? Now suppose one electron is there in the second orbit. Electron is there in the ground state and it wants to go in n is equal to 3. Then how much energy is required? If an electron is in the ground state, at the ground state, energy level diagram is completed. Now I am explaining the things related to it. If an electron has to go from n is equal to 1 to n is equal to 3, from ground state to second excited state, how much energy is required? So this energy level's energy is minus 1.51 electron volt. This energy is minus 13.6 electron volt. The energy required will be minus 1.51 minus 13.6 electron volt. And if we solve this, how much we are going to have? Let it be 1.5. 6 minus 5, 1. 13 minus 1, 12. 12.1 electron volt. So basically 12.1 electron volt is the energy required if an electron wants to go from ground state to the second excited state. Is it clear? So this is called excitation energy. This is called excitation energy. If an electron is going from ground state to higher energy state, So whatever in whatever orbit the electron goes, accordingly it is called excitation energy. Like this excitation energy is called second excitation energy. What will be the first excitation energy? You have to subtract 13.6 minus 13.6 from minus 13.4. It will be approximate 10 point something. Okay, 10.2 electron volt probably. Okay, 10.2 electron volt. So 10.2 electron volt is the first excitation energy. Second excitation energy is 12.1 electron volt. And similarly we goes on. And now what is the potential required for the same? The potential required is 12.1 volt. So this particular voltage is called excitation potential, second excitation potential. For first excitation potential, you have to subtract this from this. Okay, this is called second excitation potential. So basically excitation energy and ionization energy, they are the same thing, but ionization energy, electron comes out of the atom. In excitation, it goes from a ground state to any of the excited state, and accordingly we say its excitation, like first excitation energy, second excitation energy, and so on. Is it clear? Okay, now some more features. Let me remove all this. One question is there which is very popular, and that question is, if an electron is n is equal to 4, then how many transitions it can make? So for that there is a formula, and the formula is nn minus 1 upon 2. You have to remember this one. This is what? This is number of spectral lines. Spectral lines. If n is equal to 4, then 4 multiplied by 3 upon 2, it will be 6. It can make 6 transitions. It can make 6 transitions. From n is equal to 4, it can go into n is equal to 3, it can go n is equal to 2, it can go n is equal to 1. Now the electron which is in the 3, it can go in the n is equal to 1, it can go in the n is equal to 2, and the electron which is at 2, it can go in the 3. So how many spectral lines we have got? 1, 2, 3, 4, 5, 6. 6 spectral lines we have got. Okay, and there is no need to count. You are just put value of n and you'll get your answer. Is it clear? So this is the second point. Third point is often asked. It is often asked, what is the shortest wavelength in Balmer series or longest wavelength in the Balmer series? So remember students, for a particular Balmer series, we all know that when the higher energy state comes to the n is equal to 2, then the spectral lines are called Balmer, they belongs to Balmer series. Now for shortest wavelength, just remember, for shortest, the transition must take from n2 is equal to infinity to n1 is equal to given value. For shortest wavelength, and for longest wavelength, n2 is equal to just next to n1 is equal to given value. Like suppose if someone asks what is the longest wavelength in the Balmer series, so Balmer series is when the transition takes from higher energy state to n is equal to 2. For longest wavelength, you have to go to just next. From 3 is equal to 2, this one is going to be the longest wavelength. And for shortest wavelength, from infinity to 2, this is going to be the shortest wavelength. Is it clear? So these are some points which are related to the atomic model. Okay, this one, energy level diagram. Now there are some limitations of Bohr theory. Let us discuss those limitations and let us finish off this chapter. There are some limitations of this chapter. Okay, there are some limitations in the chapter. What are the limitations? Limitations of Bohr atomic model. Limitations of Bohr atomic model. Actually, there are so many things which the Bohr theory does not explain. The first thing is, Bohr theory could not explain is circular orbits, about circular orbits. Circular orbits. Bohr theory did not explain why circular orbits have been chosen, whereas elliptical orbits are also possible. Okay, why we should choose circular orbits when elliptical orbits are also possible? Bohr theory could not explain that. Second point, there are various spectral lines. There are various spectral lines which were not detected by Bohr theory. Okay, which cannot be explained by Bohr theory. Okay, these are strange spectral lines which Bohr theory did not explain. Third point is, there is one effect which is called Compton effect. Compton effect, in which what happens, the spectral lines splits up in the presence of electric field and magnetic field. Why this happens, Bohr theory could not explain. Okay. Fourth one, intensity. We know about the frequency, we know about the wavelength, we know about everything, but we don't know about the intensity of spectral lines, of what intensity the spectral lines are emitted. Okay. So these are some major drawbacks. And fifth one, one more. Bohr theory is fit for the atoms which have atomic number 1, like hydrogen-like atoms which have single electrons. If an atom is more than 1 electron, Bohr theory could not explain the existence of spectral lines emitted by those particular atoms. Okay, so these are the limitations of Bohr theory of atomic model. And now this is all for this chapter. We have done all the topics, and this is all for the half-yearly syllabus also. Okay, so in the revision class, let us revise the things and let us prepare ourselves for the better examinations, better performance in the examinations. This is all for the day. Thank you.